a glass of water.
I'll get you a glass of
Oh,
water
okay.
and I'll show you where.
Cool.
Nice biography that he sent out, but I won't do the whole thing. But John, after he finished his high school in New Zealand, he spent a year in Japan, and then he went to the University of Otago and studied geology. And then he worked at GNS and in Japan again for another year before starting his PhD at Stanford University. And when he finished at Stanford, he went straight into a faculty position at Victoria University of Wellington, where he's been ever since. And John and I first met in 2016 when we were both elected to the board of directors of SSA, which is the Seismological Society of America. And we both had 2 terms on that. And then John went on to become the president of SSA. And we've been, since that time, we started collaborating on many different projects in New Zealand, one on the Alpine Fault, but also in the North Island as well. And today he's going to tell us more about past, present, and future earthquakes on the Alpine Fault. Thanks, John.
Kia ora, Megan. Hello, everybody. Thank you very much for coming this afternoon. I'm really glad to be here because it's been a really productive few years of research with Megan and her group. Several of Megan's group were in New Zealand just a couple of days ago, and for reasons I can't quite explain, we've all migrated over to Canberra to continue the discussion. What I thought I'd do today is give you an overview of some of the work I've been involved with on the Alpine Fault over the last 15 or so years. And this is extracted from a lecture I've been giving up and down New Zealand over the last few months, something called the Hochstetter Lecture, which is organized by the Geoscience Society of New Zealand. And it's intended for a public audience. And I've decided to give it more or less in the same terms, although I will probably emphasize a few points that I think might be of particular interest here. Megan and I and the rest of the group started working on DAS, distributed acoustic sensing, about 3 years ago. And to put you out of your misery, I'm not going to speak about that work at all. That's another really interesting part of the work that we're doing. But today I'm going to be focusing on sort of the longer term research being done on the Alpine Fault. So what I thought I'd like to cover is, first of all, a little bit of background to the Hochstetter lecture, just to give you some context for why I put this talk together, and then spend a few minutes talking about the paleoseismic record of big Alpine Fault earthquakes. This is perhaps unprecedented, the length, the quality of this paleoseismic record, and it tells us a lot about what's to come in the future, and that motivates much of the research I'm talking about. I'll give you a brief overview of some of the projects I've been leading the last few years. The Deep Fault Drilling Project, in which we attempted to drill into the Alpine Fault to basically measure its state of health. SAMBA, SALSA, dwarfs, a number of other seismicity studies. And then, well, I'm not going to talk about the DAS, but the point is we're going from having dozens of sensors to now having thousands of sensors very closely spaced. And that's provided an absolutely unprecedented view of the fault at scales as small as a few meters. I do want to dwell on what might be to come. We have a great paleoseismic record. We think we know the state of the fault at the present day. And the really important question is what comes next. So we're looking at how we can bring together simple, parsimonious computational models of earthquake rupture with the paleoseismic data sets to say something about which way we think the fault ruptures. That really matters for ground motions. And basically trying to reconcile these very different timescales of earthquake studies. I'm going to take a few lessons from big earthquakes that have occurred in the last few years elsewhere. And then, and this is a challenge that I've been putting to the New Zealand community, but I'll put it to the global community and the Australian community here today. We really need to be thinking about what steps to take right now to instrument the Alpine Fault even better for future earthquakes. Because when the next earthquake happens, there will be signals that we would like to record, not necessarily for the local community's benefit, but for the global earthquake science community. And if we don't record them, in the case of the Alpine Fault, we're going to have to wait another 300 years. So we better get on with it. I put this in when I was speaking to the New Zealand community, mostly to provide a bit of context to parts of the talk I'm not covering today. But I just want to make the point that a constant theme of my research for the last 15 or 20 years, since I've been back in New Zealand, has been the Alpine Fault. And I'm illustrating that with a map that was produced in 1864 by Ferdinand von Hochstetter, who was an Austrian scientist who came to New Zealand and did some very influential mapping in both islands. But in this case, I'm showing a map of the Northern South Island. It has many of the features that we would recognize in the geological maps produced these days. But one thing it lacks is the Alpine Fault. The Alpine Fault is not mapped here. It wasn't, in fact, first mapped until the 1940s. And since that time, we've come to appreciate many of its characteristics. But really, it's only been in the last 50 years or so that people have started to think about the earthquakes produced by the Alpine Fault. It's a very important tectonic feature, there's no doubt about that. But its earthquake potential really didn't get much attention until relatively recently. I'd like to emphasize the sort of history of the Alpine Fault studies by putting in this map produced by Harold Wellman and a colleague, Willett, published in 1942, in which they mapped the southwestern corner of the South Island. And this map here is, again, it contains many of the features we would recognize on a modern map. The dash work that Vern and Megan and others in the audience tonight have been doing is down here at Haast. And these are the Dung Mountain ophiolites, which are offset by about 450 kilometers along the Alpine Fault, and were key to recognizing the extent of the structure. Harold Wellman was the first Hochstetter lecturer. So when I gave my lecture a month or two ago up and down the country, I really wanted to emphasize that. 50 years ago, he gave the first lecture. And as it happened, this year's lecture was the last one. Not because I did a particularly bad job, but because the Geoscience Society is changing some of its lecture series. So that's a little bit of context. Harold Wellman went on to become a staff member at Victoria University of Wellington, but unfortunately I never overlapped with him there. This slide really encapsulates a lot of what goes on inside my head when it comes to thinking about earthquakes. And I put this in here to sort of make the point that earthquakes on the one hand are quite simple, but on the other hand, particularly when we're trying to account for their temporal characteristics, they're very, very complicated. So earthquakes involve the frictional sliding between one block of rock and an adjacent one. And that process is governed by the stresses that are acting on the faults and on the rocks. And the stresses are, to some degree, compensated for by the pressure of fluids. Fluids present in the Earth's crust act to counteract normal stresses, and that reduces the effects of friction. Now, the fluids are, the pressures of the fluids are governed by how easily fluids can move through a rock mass, and that's described by something called permeability. And permeability is probably controlled by at least these three factors here: chemistry, temperature, stress, probably by time, probably by other things I'm not covering here. But the point is, it's a complicated process, and those factors are controlled at different ends of the spectrum by tectonics, by the plate tectonic regime and the large-scale lithospheric drivers, and by hydrology. And in the case of the Alpine Fault, hydrology plays quite an important role. So I'm going to show you a whole bunch of photographs, mostly taken in beautiful weather, but it really rains down there. And the rain that falls on the Southern Alps does play an important role in governing fluid pressures acting on the Alpine Fault, and therefore probably on seismogenesis. So that's a very, it's a reasonably long list, but it's sort of simple in the sense that you can see how these different factors interact. I myself was really influenced when I started my geological career by Rick Simpson, who was a professor at the University of Otago when I started. And he spent a lot of time in his career thinking about these different factors. And I've never worked with him actually as a scientist, but he was a very influential figure for me when I was trying to plan my career. So a theme that runs through this talk is that when we think about earthquakes, it's a little bit like thinking about an elephant. You know, if you have one big elephant and a number of people holding on to different bits, you have a different perspective of what an elephant really is. And the same is true of earthquakes. So co-seismic processes associated with a natural rupture, typically occur in fractions of a second, maybe up to tens of seconds, maybe a few minutes, but then they're followed by processes that might last for days, to decades to maybe centuries, the sort of post-seismic equilibration of the fault and then the interseismic processes that ultimately reprime the system and lead to another big earthquake at some point in the future. So this is sort of the post-seismic and interseismic period in here. And then over time, big faults like the Alpine Fault produce large earthquakes on timescales of hundreds of years, but to account for 450 kilometers of offset, you have to wait millennia. So the different communities of researchers working on on earthquake physics tend to be trying to study the earthquake source on one of these timescales and say things about what happens at other timescales. And that is what makes it tricky. So I'd like to sort of set the scene for talking about how often Alpine Fault earthquakes occur by just making the point that as recently as 2007 in New Zealand, we were still asking the question, does the Alpine Fault generate great earthquakes of the size of magnitude 8 or so? And this was very much a live question. And there were various arguments for why the Alpine Fault may not generate such large earthquakes, and certainly there had been none historically. So this was a live question. It was important to ask. But in the intervening 15 or 20 years or so, a huge amount of work has been done on the paleoseismic record of large Alpine Fault earthquakes. And I don't have the time or the expertise really to go through this in great detail, but I'll just explain briefly what's being shown here. This is a rotated view of the Alpine Fault. The northeast corner is now plotted on the left, and the southwest corner is down here on the right. The different colors represent different segments of the fault, which appear, based on the paleoseismic record, to have quite characteristically different rupture histories. And the bulk of the diagram here is showing you at a particular location, in this case, Lake Parenga, showing you the time of individual events inferred to be earthquake rupture. Now, establishing a chronology at one location is tricky enough, but in order to really say anything about what that represents in terms of a large earthquake source, you have to be able to reconcile this record with another record, in this case at Lake Hanyere, given that there are timing uncertainties in all of the different parameters and you're extrapolating across great distances, and you have some gaps in your data. But nevertheless, this is, as of 4 years ago or so, the biggest compilation of paleoseismic information. And what it reveals is that the Alpine Fault and the central and southwestern sections in particular produce earthquakes remarkably regularly. It's not clockwork, but the recurrence interval for the central Alpine Fault is something like 260 years, plus or minus about 60. And when was the last earthquake? The last earthquake was in 1717, so 308 or so years ago, and that, as far as we can tell, ruptured the whole on-land section of the Alpine Fault. Whether it started down here and ruptured towards the northeast or did the opposite, we don't know, but I'll return to this point later. But I've already given you two pieces of information that are pretty important in thinking about the context for Alpine Fault research. One, it produces earthquakes remarkably regularly on a timescale of something like 260 years plus or minus something. And secondly, it's been 308 years since the last earthquake. And so those two factors together mean that we are very late in what is a very well-determined interseismic cycle, and we would expect the next earthquake in the coming years or decades.
John,
yes.
What was the length of that section?
That's about 400 kilometers. There's but there's 350.
What's the vertical axis? I'm sorry.
The vertical axis, sorry, I should have said. The vertical axis is time.
Time.
This is a chronology going back 2,000 years, 4,000 years from the present day. This is 2000 BC. And each one of these is an earthquake as inferred at a single location. I should have said the horizontal bars link measurements thought to represent a single through-going earthquake. And just from looking at this, just doesn't matter which one you pick on, but you should be able to see that there's a reasonable degree of regularity in the spacing of these things. This is a dark art. I hope there are no paleoseismologists in the room, but this is a very dark art. But nevertheless, the figures that come out, which I'll summarize in the next slide, are somewhat sobering. So without going into all the details and realizing there's a lot of words here, the last major Alpine fault in 1717 ruptured all three of the principal sections on land. The recurrence interval is something like 250 years or so. If you take those two numbers and do a conditional likelihood of the earthquake happening in the next 50 years, it's something like 75%, although there are admittedly wide bounds on that number. If you do simulations based on rate and state friction and run a whole lot of different sort of scenarios, there's something like an 80% probability based on the paleoseismic record that the next big earthquake will rupture both the central and the southern sections, and that would definitely be bigger than magnitude 8. Now, the other thing that's come out of the paleoseismic record is that there are certain key points along the fault, namely the intersection between the southwestern and central and northern sections. These intersection points play a particularly important role, it appears, in the nucleation and the termination of earthquake rupture. So earthquakes preferentially seem to start and to stop there based on what's found in the paleoseismic data. So I'm particularly interested in what the factors are that control the location of where earthquakes start and where they stop, and the timing. It's one thing to say that the earthquakes happen every 250 years or so. That's important. But what is it that controls that time? Why is it 250 years and not 500 years? So that's a sort of context for the work that I'm about to describe. Recently, we've had a study going in which we've started to take that information and say, okay, what's going to happen next time? And this is a very simple slide in the sense that it's designed to convey a simple message. And it basically is an attempt to say that it matters which way this fault ruptures, where it starts, and where the slip occurs. So here are three very simple scenarios. This is an idealized representation of the fault. Here it's about 500 kilometers long. In scenario A, the earthquake starts at the northeastern end. It propagates southwards, and most of the slip occurs at the southwestern end. Scenario C is just the opposite. It's flipped around. And scenario B is something in the middle where it starts in the southwest and it ruptures towards the northeast. And these traces on the right-hand side are synthetic seismograms calculated for Christchurch, for a spot in Christchurch, just making the point that even with such idealized models, you can forecast very, very different shaking scenarios. So in scenario A, when it starts in the northeast and ruptures south, you end up with a very long duration of shaking, but the amplitude is very small. On the other hand, if you start it in the southwest, you rupture it along the South Island in the direction of Nelson, Wellington, you have a compressed record of strong shaking and amplitude is much higher. And of course, if you have something in the middle, you get something in the middle as well, both long durations and strong shaking amplitudes. So this matters when you're designing infrastructure, when you're planning for the effects on the community, you need to know what sort of shaking is likely to eventuate. And that is something that only really in the last 4 or 5 years have we started to grapple with. This is another way of looking at it. This is just looking at the ratio of peak ground velocity that you would get based on rupturing from the north. In this case, if you ruptured from the north in this direction or you ruptured in the south in that direction, you get quite different patterns of shaking. You amplify the ground shaking by a factor of about 1.5 to 2. And this is what happens if you compare a rupture from a central location, from about the location of Haast, versus a southern hypocenter, and you get a slightly different pattern. The point is, here are a couple of scenarios that we've thought about, but of course, there's myriad possibilities. The way the Alpine Fault ruptures next time need not be described by any of these models, and ideally, we would be able to incorporate that in our forecasts of shaking hazard. Okay, so with that sort of background, what I thought I'd do is just whip you through some of the experiments we've been doing in the last few years. And I'll start with the deep fault drilling project, which began in 2011, and was an attempt to address some pretty big questions about one large fault and see whether we could generalize that to others. So we were interested in questions like how the Alpine Fault and perhaps other big faults had evolved, how their physical properties govern their behavior during earthquakes, what factors, sort of baked-in factors like the structure of the fault zone and changing factors like fluid pressures and stress, what factors control the timing of earthquakes, And basically, like I mentioned earlier, we wanted to measure the state of health, the temperature, the pressure, permeability, and the stress in and around the fault zone late in this well-characterized earthquake cycle. So as you can tell from the grids, we achieved some of our objectives at least in the first phase of drilling. We drilled through the fault, as I'll explain, and then things came to a crushing halt several years later. So we started small in 2011 in the first phase of drilling called DFDP1, and we went to a location called Gaunt Creek. Is there anyone in this room that's been to Gaunt Creek? A couple, well, one person did his PhD there, but Gaunt Creek is a classic location where in the 80s, it was recognized that we had a fantastic Alpine Fault earthquake, which actually doesn't look like this at all anymore, but we had an Alpine Fault outcrop, in which the hanging wall was bringing up mylonites from a depth of 20 or 25 kilometers up to the surface and thrusting them out over modern gravels and being eroded and forming those gravels. So there's a huge juxtaposition of structural depths here. The mylonites are coming up faster than they know what's happened to them in a couple of million years or so, being eroded and laid down as gravels. And along the fault itself, there's a zone of crushed rock, cataclysites, which represent the upper crustal brittle deformation of the mylonites as they move up towards the surface. So we went here and we tried to drill 2 holes, and we did drill 2 holes just a little bit upstream with the idea of intersecting the Alpine Fault somewhere where we knew it to be at a very modest depth, only 100 or 150 meters. And the idea was to measure its properties in a sort of pilot study before we went any deeper. So we did that. Here's the outcrop represented again up here with the mylonites, the cataclysites, and the gravels. And we went up the river and we drilled 2 boreholes, one about 100 meters deep and the second about 150 meters. And fortunately, we intersected the fault in both boreholes and made some really important measurements. So you might say, at 100 or 150 meters, what does it matter? Well, good point, but we wanted to show that we could do it. And while drilling, we made some really interesting measurements about things like permeability. So the permeability of the rocks forming the hanging wall, if we go more than a few tens of meters away, is something of the order of 10 to the minus 14 meters squared. Now, that's perhaps not a number that means very much to most of you, but if you get closer to the fault, within about 30 meters of the fault, the permeability reduces by a factor of 1,000. And if you go right into the core of the fault here, the fault core where there's a layer of gouge, the permeability is lower than 10 to the minus 19 meters squared. So that's a millionfold reduction in permeability over the space of a few tens of meters. And then if you go into the fault wall, permeability goes up again to something like 10 to the minus 16 meters squared. So this is important because the fluid pressures that are going to build up, at least if this was pertinent to the deeper fault, the fluid pressures that build up are going to be governed by that very strong permeability gradient as you approach the fault. We knew there was a fluid pressure differential across here because when we drilled across it, there was a big sucking sound and we lost all the drilling mud because there was a several MPa pressure difference across the fault. So even at these shallow depths, we were seeing things about the core of the fault that are of relevance to the earthquake machine because they probably bear on fluid pressures at greater depths. Okay, then we decided to go a little deeper. We intended to target the fault at a depth of about 1 kilometer and to drill further into the footwall, into the Australian plate, to an ultimate target depth of about 1,300 meters. So this is the second phase of drilling, DFDP2, which took place in a valley called the Whaturoa Valley in 2014. The Whaturoa Valley is formed by the Whaturoa River, which is one of the biggest rivers on the west coast of the South Island and drains a huge volume of the central Southern Alps. And when this river is in flood, you know about it. It's a very, very big river. So we were there for several months and we drilled down to an ultimate depth of about 900 meters. We did not go through the fault. We had a casing string failure just before Christmas in 2014, which meant that we lost the bottom of the borehole and we could not continue drilling. There will be a whip around later because we're quite keen to go back, but we didn't get through the fault. We got to within probably about 200 meters of it. Nevertheless, we made some really interesting measurements. And the one I want to draw your attention to is the geothermal gradient. So this black line, this is a depth versus temperature diagram. The black line shows you the temperature measured down the borehole using an optical fibre and a technique called distributed temperature sensing. And we measured the temperatures all the way down to the bottom, down to a true vertical depth of about 800 meters. And I've just put in this red line here, this dashed line, to indicate the overall gradient measured over the top 100 meters or so. And the gradient that we get out there is something like 125 degrees per kilometer. 125 degrees per kilometer is about 4 times the global average geotherm. So this is not a magnetic system. There are no volcanoes around. This is a purely tectonic setting. And nevertheless, we've got these extremely high temperatures. So we were approaching 100 degrees by the time we got down to 700 meters. I put that in context here. This is a cumulative distribution of all the geothermal gradients measured in deep 500 meters or deeper boreholes worldwide. This is geothermal gradient along the horizontal axis and the cumulative distribution of the vertical axis. And as I said, the global average geotherm is something like 30 degrees per kilometer, which is here. Some other big fault drilling projects have encountered geothermal gradients between about 20 degrees per kilometer in the case of Wellington and maybe 40 degrees per kilometer in the case of Parkview. But the Alpine Fault is off the charts. It's way over here at 125 degrees per kilometer. Why is that? As I said, no volcanoes, no magma. It's because basically we have 2 types of advection occurring here. We have rock advection. The Alpine Fault movements are bringing up the mylonites, as I said, from great depth below the Southern Alps. They're coming up something like 20 or 25 kilometers in just 2 or 3 million years. And that brings very hot material up into the shallow crust before it can cool. So that's one type of advection. The second is the advection of groundwater. So to go back to the water story, the water falls on the mountains, it seeps down as groundwater, it goes down beneath the mountains, up in the river valleys, and it mines heat out of these hot rocks. And so what we are seeing is the combined effects of rock uplift, rapid rock uplift, and large-scale fluid circulation. Now, those high temperatures probably affect behavior of the fault. I mean, when you get to temperatures of 100 degrees and only the first few hundred meters, if you think about what happens a little deeper, we are getting into temperatures that some people would think of as diagnostic of the bottom of the seismogenic zone within only a few kilometers of the surface. So we need to understand what the ramifications are of high temperatures for the rheology of the fault. We also made some observations, which I might just quickly mention. We made some observations of the basic geometry of the fault, recognizing that this is a dipping fault. It's a high slip rate, very mature fault. And as far as we could tell, albeit only from drilling through the hanging wall, we have this very asymmetric structure with a damage zone, a fault zone, damage zone that is up to several thousand meters wide. There's one other measurement I'll mention, which I'm not going to show you the observations that underpin it, but if someone had asked me following the drilling, could you say anything about which way the fault might prefer to rupture? Based on some of the measurements we made downhole, we would say, yes, we think it preferentially ruptures from the southwest to the northeast. And I'll return to that a little later. But that was what we got out of the drilling. Now, to go much deeper than that, at least in New Zealand over the last few years, what we've done is deploy seismometers and use mostly micro-earthquakes, micro-seismicity, to say something about how the fault is behaving at greater depths. And so in this diagram, which is again another rotated view of the fault, this time flipped around, this is the northeastern end, this is the southern end down here, and each one of these collections of colored dots represents a temporary, mostly temporary seismic network that's been put out largely with student labor for periods of time between just 6 months or so in some cases and many, many years in other cases. And this is I think worth emphasizing, this is a very interesting area to do field work. The students, and there's at least one in the room here who can probably attest to this, they have to get used to working on scientific problems in pretty remote areas. There are helicopters involved. There's a lot of working with landowners, with the Department of Conservation and so on. And so it's something that we've put a lot of effort into over the last few years so that people come out knowing how to do field work in remote places. I'm not going to go through all of these in great detail, except to say that some of them, in particular, one of the networks that's operating in the middle here, have now been operating for about 17 years. So one of the things that we can do with the data from these networks is to look basically at just where the earthquakes are in depth. And here is yet another profile along the Alpine Fault. In this case, just for the central section, centered roughly on Aoraki, Mount Cook, the highest mountain in New Zealand, which is indicated by the cross. And what we're showing here in the grey dots are just the depths of earthquakes projected onto a vertical section. This is actually work that Konstantinos did as part of the first phase of his first and third phases of his PhD. And what you can see just by looking at the grey dots is that, you know, they go down to a depth of something like 20 or 25 kilometers at the northern end and something comparable at the southern end. And in the middle, seismicity is compressed to a much shallower interval. And so that's one observation. The second observation, not really illustrated here though, is that we have seismic tremor that occurs beneath Aoraki Mount Cook. So tremor, which is a somewhat enigmatic seismic signal that seems to be diagnostic of deep, slow slip, is occurring beneath the microseismicity, beneath the area of most rapid uplift. Now, what Konstantinos did in later stages of his PhD was to try and develop a thermal model of what was going on here that related the exhumation of the Southern Alps to the distribution of seismicity. And one of the products of that modeling are the isotherms, which are shown in the red lines, which are plotted here on the cross-section, on the profile. And so what this was an attempt to do, and I think it was really illustrative, was to say, okay, using earthquakes, what can we say about temperatures on the fault system? And that's what this work here has done. So that gives us some idea about the rheological difference that probably exists between the portions producing microseismicity and the deeper portions. And I'll return to the question of tremor a little later. So most recently, the array we've put out, mostly University of Wellington staff and students, is this one called the Southern Alps Long Skinny Array. And this is called this because it is both very long and very skinny. It runs from Milford Sound, way down here, all the way up along the old land section of the fault to Maruia, or Springs Junction, which is up there. So it's about 450 kilometers long, and we purposefully put out a seismometer about every 10 kilometers, preferentially on the hanging wall side, on the Pacific side of the fault, for various reasons. And we operated this for 2 years. So this was an attempt to acquire a particular data set that we could use for analyzing future ground motions, but it also enables us to look at the distribution of seismicity and tremor and other phenomena for the first time with an array which is pretty uniformly sampled along the entire on-land section of the fault. Previous arrays, like I showed earlier, had just been sort of local things and sometimes only operated for a few months. So that was SALSA. This is what the installations looked like. Basically, we were installing mostly broadband sensors in a hole, usually about 1 meter deep or so. And the practice that we use is to dig the hole until we know we're in rock, then line the bottom with coarse quartz sand, put in a paving stone, and then tamp it down really securely so that we've got a very level, very secure foundation here. We don't use cement. We put the sensor on top of that. We put a bucket on top of that to stop the water dripping on the cable, and then we run everything out to the surface. There's a lot of weather to deal with here. It snows a lot in the winter. There are birds which like to chew on all the cables, but we had absolutely fantastic performance from the sensors, and basically they all recorded continuously for the whole 2 years. So that was great. Here's a picture of some of the team. This is obviously taken at the beginning because they're smiling. It was a very, very big effort. And in retrospect, it was something I wouldn't do again. It was a huge amount of work. Putting these sensors in, digging these holes on tops of mountains, and in farmland was really very intensive. You can see sometimes we were working in snow, other times we were working on farmland at basically what is peak sandfly height. Sandflies just love this, the moisture in the shallow soil there. So when you are digging holes, it's really miserable, at least by New Zealand standards. Anyway, the equipment worked really well, and we got great data. So I just want to say that the two main points of running SALSA were, first of all, to be analyzing, and I won't explain this in detail, but analyze using noise, the ground motions we would expect for future earthquakes. So effectively what we were doing is using this very regularly spaced network to establish Green's functions between points along the Alpine Fault and population centers throughout the South Island. That's what's illustrated here on the right. But secondly, we were using this array, which is now again shown in a rotated format. We were looking at the propagation of waves along the fault for tomographic purposes and other things, but also just looking at the distribution of earthquakes and tremor. So it's been a really fantastic resource. And we're still working our way through all the data. I'm just going to put this in as one quick snapshot of what we've been looking at. As I said, we've had profiles of the seismicity before, but generally they've been quite confined in their long strike extent because the networks that underpin them have had different characteristics and operated at different times in different places. But for the first time here, we're basically looking at seismicity along most of the on-land section. Those are the grey dots in both of these figures. D5 and D95 are the 5% and 95% depth lines, because we're interested in how deep the seismicity goes based on Konstantinos's work. And then in blue are shown the locations of seismic tremor. Seismic tremor has previously been reported on the Alpine Fault, but when it was, we were always a bit concerned that we could only see it where we had really good network coverage. And when it stopped, we weren't sure if that was because we ran out of seismometers or ran out of tremor. But in this case, we're very confident that we are seeing tremor in some locations, like here and here, but not in others. And so the lower figure is just superimposing this on a map or on a profile of QP, the inverse of P wave attenuation. And we clearly have some association of the tremor with this low QP structure down here, but we haven't yet gone into details of what that might mean. So one of the advantages of having this network running at the same time with the consistent spacing along the length of the fault is that we, for the first time, have a fairly homogeneous collection of earthquake and tremor observations. I'll just return briefly to one of the segment boundaries that I mentioned earlier. This is down southwest of Haast. Haast is where we've been doing the DAS work over the last couple of years. And this is an interesting place because, like I said, these boundaries between the southwestern segment of the fault and the central segment appear to be where earthquakes preferentially start and stop. And the two models illustrated on the right here are two attempts to explain what the connectivity of the fault structures might be down there. Either you have a single continuous surface, as illustrated in the upper figure, with a fairly abrupt but continuous transition there, or potentially, and there are good reasons for thinking this might be the case, you have a dipping fault characteristic of the central section of the Alpine Fault and a subvertical fault characteristic of the southwest, and they overlap partially in a zone here. And Peng's been doing some very interesting work on receiver functions using small seismometers called nodes that were put out in conjunction with the DAS experiment. I'm just illustrating here another set of receiver function results done by a group from the University of Edinburgh, and they've been looking at receiver functions on larger scales than Peng's work, but they seem to see changing patterns in the receiver functions indicative of a subvertical structure and a dipping structure. So maybe of the two models that are illustrated there, the one that this would sort of favor is the overlapping fault model. Right, now, what I want to do for the remainder of the talk is just talk about where we're going with this. So we have a fantastic paleoseismic record. We have the ability to synthesize the ground motions associated with different earthquake scenarios. And what we're interested in doing is trying to use the paleoseismic record, not just to date earthquakes or to tell you about their extent, but also to use the pattern of inferred shaking to say which way the Alpine Fault has ruptured. So I won't go through this diagram except to say that when paleoseismology experts are doing their measurements, they're collecting cores from lakes. They are looking at the stratigraphic record in the core, and they're able to determine where they have an earthquake event followed by various processes of sedimentological response. And if you think paleoseismology is a dark art, then this sort of business is even more. But it enables them not just to date when an earthquake has occurred, but also, based on what sorts of catchment responses they see, to say something about the strength of shaking. So here are a bunch of lake sites along the Alpine Fault, illustrated in blue. And what we'd like to do is try and use the measurements to say something about which way the fault ruptured. Before I get to that, here's a summary of the on-fault measurements. These are measurements for the most recent earthquake in 1717, which tell us where we think the fault ruptured. And you can see that at each of those 5 locations, it looks as if the fault ruptured through that zone. That's how we infer that the entire length of the fault ruptured. So we've got that information for the 1717 earthquake. We know it ruptured this big, long extent. Based on the paleoseismic measurements made in the cores, we can put some estimate of the level of shaking intensity at each of these lakes. So, for example, at this one right down here in Newland, the shaking was less than intensity 8. At this location shown in red, it was higher than intensity 8, and so on up the length of the fault. And you might say, well, gee, there must be a lot of uncertainty in these measurements, and there is. So we are looking at the overall geographic consistency to see whether those measurements are diagnostic of one rupture direction or the other. There's one other ingredient we need, and that is to say, okay, we're going to model ground motions in a computational model, but we have to let the earthquake off somewhere. Do we let it off in the south and have it rupture this way, or at the north and rupture the other way? Do we set it off in the middle? Or, as it happens, we have a preferred location, which happens to be quite close to Haast. Maybe we let it off there. And so with those ingredients, we're able to basically run computer simulations and say, if it started here and it ruptured in this direction or that direction, what pattern of shaking would we observe? And is that compatible with the paleoseismic data set? So this figure is very complicated, but basically, I'll explain what it's trying to do. This is mostly for the researchers' purposes rather than the public. But these are the different lakes from south to north. Plotted here in the different colors are in red the paleoseismic estimates of how much shaking intensity there was in each lake. So in this case, the intensity was less than about intensity 7. In this case, it was more than intensity 6 point something. And in gray, these are the results of the computer simulation. So if in the left-hand column, the earthquake started at a preferred location and ruptured, well, actually, I'll start with the easy one. I'll start with this one. If it started in the north and ruptured south, then the pattern of shaking we would expect at each lake is shown in gray. And to make it easier for you, I'm just going to show you the cases in which the simulations do or do not agree with the paleoseismic observations. So where they've been crossed out, this indicates that the paleoseismic observations are inconsistent with what we would model if the earthquake started in the south and ruptured north, and if we measured it at a particular lake. And what you can see, I hope, from this is that at about 5 out of a dozen locations where we have measurements, we're discrepant. If it started in the north and ruptured south, then we can only account for about 7 out of 12 of the measurements that we've got in the paleoseismic data set. On the other hand, if it started in the south and ruptured north, we can account for all but one of them. If it started in the middle, we can account for most of them, but not all of them. And if we set it off at our preferred location, for reasons I won't go into, again, we can account for all but one of the observations. So what does this mean? It means that based on this analysis, we think that the last earthquake started in the southwest and ruptured towards the northeast, ruptured towards Christchurch, towards Nelson, towards Wellington, towards the bigger population centres. So there are our two sort of winners in a sense. We can go one step further and say, right, we have really good data for the last 4 earthquakes for these paleoseismic shaking intensities. What do these data tell us? And if we analyze all 4 of them, we come to the conclusion that it's most likely that the Alpine Fault earthquakes of the last 4 big earthquakes have either ruptured from the south unilaterally towards the north, or they started somewhere close to the south and ruptured bilaterally. We don't have any evidence of the earthquakes starting in the north and rupturing south. And this is the first time I think we've been able to actually put directivity onto a paleo earthquake and say something about not just in one earthquake, but in 4 earthquakes, which way we think it's gone. So just to wrap up then, I want to talk about the future. So we're moving into this phase of trying to reconcile paleoseismic observations with the way we model earthquake rupture. And I just want to talk about what that should mean for the coming years and decades. So what I'm going to think about is the observations we've got paleoseismologically, some measurements made in other parts of the world during other big earthquakes, because when it comes to big earthquakes, fortunately, they are reasonably infrequent, but that means we need to combine our data sets wherever possible. And thirdly, we're going to think about how we fold into this our measurements made of the current state of the fault, variations along strike, down dip, whatever it might be. So I'm going to show a couple of slides from the 2023 Turkey earthquakes, the doublet of earthquakes that occurred on the East Anatolian Fault in February of 2023. These were hideous earthquakes in that they killed something like 55,000 people. And what was unusual is that they, among other things, is that the earthquake, the combined effects of the earthquake were very complicated. The first earthquake, which was magnitude 7.8, started on this little fault here, ruptured up towards the East Anatolian Fault, and then ruptured bilaterally. And it was followed only a few hours later by a magnitude, I can't quite remember the magnitude, 7.7, I think, earthquake a little further to the north. Now, these, based on the distribution of slip with depth and the length of slip, are considered to be reasonably useful analogues, particularly the first of these 2 earthquakes. And so a colleague of mine, Carolyn Holden, is working to try and understand how we can bring this information back to New Zealand. So what I want to illustrate here is the fact that it's now possible, and this is work by Alice Agnes Gabriel, now at Scripps, it's now possible to simulate in supercomputer simulations extremely sophisticated models of earthquake rupture. And this is Alice's group's efforts to explain the first of the earthquakes there. It's a very beguiling representation of what happens, and it can account for a number of different features of the rupture. But one thing that these models do not incorporate, because the observations simply haven't really existed, is measurements made right along the trace of the fault. Ideally, we would make measurements there because they constrain certain aspects of the rupture, which are very difficult to obtain otherwise. So here's an example of why those sorts of measurements matter. This is the startup phase, the nucleation phase of the first of the big earthquakes, magnitude 7.8. Started here, like I said, ruptured just a few tens of kilometers on a short fault before spreading bilaterally. And these 2 traces here are showing velocity records from strong motion sensors, which are within a couple of 100 meters of the fault trace. So they're basically right on the fault trace, and they see features, in particular, this big velocity pulse here, they see features which are indicative of super shear rupture. And this is intriguing because in this case, it seems the earthquake started to propagate at faster than the shear wave velocity within only a few kilometers of its initiation. And using these observations, you can account for some of the very strong shaking which caused so much devastation in Turkey and Syria. So these sorts of measurements are absolutely important for understanding some of what transpired, but they are very rare. I'll skip that. Here's another record, which I'm sure everyone in the room has seen. Has anyone not seen this? No. This is a pretty amazing record. This is the video record from the Myanmar earthquake in March. This is work by Jesse Kearse, who's a former student of ours at Victoria, who's now based in Japan with Yoshi Kaneko. And like all of us, he looked at the video on YouTube and he thought, this is a fantastic video. But unlike, I would say, 99% of us, he then said, can I extract useful information out of this? And so what he did is he used video analysis techniques to basically infer the relative motions of all of the different pixels in these different frames. And using that, he was able to extract a profile for the velocity, the slip velocity, as a function of time of the right-hand side, far side of this with respect to the near field. And this is the first time this direct observation has been made of the duration of slip as the earthquake rupture propagated past, in this case only about 2 seconds, and the speed of that slip. And in this case, it was about 3 meters per second. So this is a very unusual record. We could look at it all day. It's got lots to keep you focused. But the point is, this is an absolutely near field observation of what's going on in a fault, and we lack them in so many cases. So I just want to finish by saying, okay, we've seen the benefits in the case of Myanmar for making measurements which had previously not been made. In the case of Kahramanmaraş in Turkey, we've seen what can be inferred from strong motion records made right around the fault trace. What should we be preparing to record in future earthquakes, and where should we try to do that? So I'd like to make the case that the Alpine Fault is something we know a lot about. We know a lot about its chronology of big earthquakes. We know a lot about its current state, and we think we now know something about which way it might tend to rupture. And so the question is, what should we be doing? What measurements should we prepare to make to take full advantage of an earthquake that we think is quite likely? So I have for you a time-limited offer. This is the Alpine Fault viewed from offshore, looking up towards the north. There's the trace, and the offer starts here. What I'd like to do is to go to a spot on the Alpine Fault and basically instrument it like crazy. Here's the trace again, and we could put out all sorts of things. We could put out in various colors, strong motion sensors in blue, GPS in orange, broadband in red, pressure and temperature sensors in green, and we could do that at different positions with respect to the trace for various reasons. At 10 meters from the trace, at 100 meters, at 1,000 meters, and we could sit there and wait and record what happens when the earthquake goes ripping by. Now, the problem is, despite what I said earlier, we don't absolutely know which way the earthquake is going to rupture. We don't know exactly where it's going to start. And therefore, we couldn't just do this once. We have to do it in many locations. So there we are. It's something that we could go out, and with the right level of funding, we could do right away. And that would provide absolutely unprecedented data in the event of what we think is fairly likely. I mean, the fault might not rupture for several years. It might not rupture for decades. But in this case, we are confident that we know quite well how often it ruptures, and we're getting close. Of course, it might have started already, but we won't know for a few minutes. Now, unfortunately, this is a real stretch goal. You know, we'd be in it for the long haul. We could be in it for years. It might be decades. It might even be longer. But based on the record of big earthquakes, we expect it in the next few decades. It would be an intimidating funding proposition, to put it mildly. And without trying to create a trans-Tasman row, the science sector funding in New Zealand does not make it easy to contemplate something like this for the next few years or decades. We'd need to spread our bets. We'd need to do it at many locations along the fault in order to be confident not to miss it, because that would be hugely embarrassing if it started just over there and ruptured the wrong way. And we really would need to be making important measurements from day one. We couldn't just sort of pin this all on waiting for a big earthquake and then say, I'll just wait until then we'll deliver something. So it's a challenging sort of project. Now, those of you who've been to New Zealand may know that we have ferries that take us between the North and the South Islands, and those ferries quite routinely break down. And the current government, when they came into power, said, we're not going to go for the Rolls-Royce option. When we buy new ferries, we're going to go for the Toyota Corolla. And so this is the Toyota Corolla option for the Alpine Fault. And that is to put out strong motion sensors on either side of the fault every 10 kilometers, for example, along as much of it as we can cover, and also put out cameras. And there's a third piece of equipment needed. Can anyone tell me what the third piece is? Lights. Because it would be embarrassing if it happened to happen at night and the cameras couldn't see anything. So someone pointed this out to me, a member of the public, and said, oh, you've got to make sure the lights are on. Yeah. But this is something that could be done with a much smaller budget, and it would nevertheless provide valuable information. So going back to the map that Harold Wellman made, I just rotated the arrow to its relative correct position. We could be putting sensors out along the length of the fault at modest cost. And we could, if we bought the right sort of equipment, we could keep it running at a modest cost as well. And in the event of the earthquake that we think is coming, we would hopefully record an absolutely phenomenal data set. Now, this is the petrol station in the small village of Franz Josef, which is basically in the middle of the central section. Franz Josef is a big tourist destination. It has the only petrol station for quite a way. And this petrol station sits right on the trace of the Alpine Fault. The fault goes through the main road here, it goes through the back of the petrol station and through a hotel at the back. And there is a camera here. It's operated by the roading authorities, but unfortunately it faces the wrong way. So, you know, you can imagine that with a small investment, you could go here and put out some equipment and keep it operating so that when the fault did rupture, if it happened to rupture through here, we would catch it. So, to summarize then, the Alpine Fault's paleoseismic record reveals, you know, a remarkable chronology of big earthquakes going back many thousands of years. And the chronology is remarkable not just because of the number of earthquakes it contains, but because of the timing of those earthquakes. Like I said, it's not like clockwork, but it's remarkably consistent. Big earthquake upon big earthquake. And what we know from that, given that the last earthquake was 300 and something years ago, is that we are well into the late interseismic phase. We're well into a well-described tail of this distribution. So we've been making measurements of various properties, both using seismic networks and using drilling and other sorts of observations, geodesy, for example, which I didn't talk about. And that reveals variations in the structure of the fault and its geometry, where it's currently slipping, where it's not, etc. And ideally, those sorts of observations should be incorporated in rupture models. I didn't say this, but the rupture models generally, unless they're retrospective analysis of real events, they incorporate incredibly simplistic descriptions of the faults, and we need to overcome that. I didn't talk about that, but there are opportunities, obviously, to do lots and lots of interesting stuff across faults here and elsewhere. Now, we don't know where the next earthquake is going to start. We don't know with absolute certainty which way it's going to rupture, but we are beginning to make some progress in trying to tease out the direction in which past earthquakes ruptured. And it could be that it ruptures sort of randomly each time. But at the moment, the last 4 earthquakes we've observed give us a fairly consistent picture of which way it seems to rupture. And just the final point, I really think that the global earthquake science community should be looking at this and other faults, but this one in particular, to ask themselves and do something about this question of preparing to instrument a fault or instrumenting a fault to prepare for a future earthquake, so that when it happens, we make the measurements that we think are particularly important for understanding earthquake physics. And I'll leave it there. Thank you.
Questions for John? Light.
Richard.
I have 2 questions for you. Does the start of the earthquake, the center, the propagation, coincide with the change from vertical to dipping orientation of the fault?
Yes, the transition between what's called the southwestern section and the central section does have a big change in geometry. We know that the central section is dipping southeastwards beneath the Alps, and the southwestern section is subvertical. And we know roughly where we know quite well where the transition is, but we're not actually sure what the nature of that geometric relationship is. But that is a point where earthquakes tend to start and stop.
Okay.
But they don't always start there, and they certainly don't always stop there. Some of them rupture through that area and some get stopped. So whether that's because of the direction they're rupturing or other factors, we don't yet know.
Right. Second question was the temperatures that you're possibly approaching in that upper plate due to crustal flood look like they could approach melting of the rocks. If you look at the projection of your thermal gradient, so you could be reaching 700 degrees or 650 within the crust.
Yeah, so
but you don't see any sign of that, do you? That there's some melt?
No, we don't see any sign of melt. But two things I'd say. One is that probably we can't just, despite what I said, we probably can't take that geotherm and just extrapolate it. And we have evidence that it rolls over and goes to a less extreme gradient. But yeah, so we don't have, we certainly don't see evidence of melt or, other gases or whatever it might be, isotopes that might tell us that something's happening like that. But we do see, a very shallow transition from seismicity to no seismicity. And, that is diagnostic of some sort of rheological boundary. Typically, that's inferred, to relate solely to rheological properties. And it seems to be at about 8 kilometers. So below that, maybe it's basically behaving plastically. Whether a big earthquake cares about that, I don't know. I mean, when an earthquake gets a head of steam up and comes racing through the Central Alpine Fault, whether it cares that in the preceding few decades all the earthquakes have been squeezed up to the surface, I don't know, because if you rupture a hot Morrow bar fast enough, you can break it. So that's work to be done. But yeah, it's very, very warm. There are hot springs all the way along the fault, I should have said, but.
I have a couple of questions, and if there's someone. It's kind of following on to what Richard's questions were. One's a very short one, but I'll start with the second one. So being so hot at the north, is there any indication that that is different farther to the south? Is it due to the dip of the the Alpine Fault? Do you expect the geothermal gradient to be significantly deeper or different to the south? Yeah,
so you should talk to your postdoc. The area of fastest rock uplift is definitely confined to a section of the fault which is probably about 80 kilometers wide. It's between the Wanganui and the Karangarua rivers, and all the evidence from thermochronology and from that sort of work that Konstantinos has done indicates that the geotherms drop off a lot in both directions. And when you get down to Haast and beyond, the fault is effectively almost pure strike slip. And there's little evidence for uplift. So, I mean, that doesn't mean the geothermal gradients couldn't be quite high, but the mechanism for producing high gradients will be different down there because I don't think you have the rock uplift.
And is the temperature or the rheology difference part of this, the models for preferential rupture northwards?
No.
Is that built into the?
No, at this point, so at the moment, the models that are being used to try and do that sort of reconciliation with the paleoseismic data, those are very simple kinematic models. And they, despite what I said about the importance of incorporating all that sort of information, they don't do that at all. They're very simple.
The last very short one, is there creep anywhere along the fault?
There are places where there is definitely not creep. And I'm not trying to be obstructive, but we know that the fault is not creeping at the surface based on the fact that roads and fences and other things are not deformed. And there is an infamous location called Everson's Wall at Marui at the northeastern end, where Frank Everson, who's the first professor of geophysics at Victoria, decided to prove this once and for all by building a big wall across the fault. And he did that in the 60s, and the wall is dead straight. It's never crept. So we know a number of places where there's no evidence for creep. At the southern section going south of Haast and Jackson's Bay, first of all, there are some unusual minerals, and secondly, some of the geodetic data suggests there might be a little bit of creep, but it's not well resolved. But if it is happening, it's down there somewhere. Good.
I think all the geometry questions for a different discussion, but I have two questions along. It's the same idea of British State plans to put GPS stations as well along the fault. The second question is more like, what has been the idea of early warning system and all?
Yep. Yeah, good question. So for geodesy, there is a sort of backbone network of geodesy, which is pretty coarse, and it's useful for looking at large scale deformation velocity. That's a continuous network. The campaign network is surveyed every few years, and that's very, very dense, but it's obviously not so great for other things. And the University of Otago has run, and it's getting to this creep question, they've run a semi-continuous network on the southwestern section for many years. They go back every few years to the same spots and leave their equipment for a long time. So that's happening, but the geodetic coverage is less good than you might hope. INSAR has proven tricky so far. There is work being done now with longer wavelength platforms, but there is, as far as I'm aware, no great INSAR insight into what's going on. With early warning, so in New Zealand at least, there is no sort of official early warning system. GNS Science, or Earth Science New Zealand, and Massey University in particular are doing a lot of work in this space. And this is a slight philosophical disagreement here, but they are trying to do it for earthquake sources anywhere in the country. And I can see their point of view, but here we have a fault which, you know, if it unzipped from Haast towards Nelson would give you 2 minutes. So you might want to have a side project which is looking specifically at earthquake early warning on the Alpine Fault. And at the moment, there's no sort of systematic work being done on that, or at least no systematic program to turn it on. It's an obvious thing to do, but yeah, you couldn't put all of New Zealand's early warning systems into that earthquake. We'd need to be able to account for a whole bunch of other ones, and that's at the moment where the emphasis is being placed. And of course, there's Google, you know, the Google Android system as well. Was that a hand? No.
Do you have a second question?
Oh, much.
Okay. So what is GNS doing in terms of relating to potential hazard in the actual communities of either Southern and North?
Yep.
I mean, does that the last statement you make there, the global earthquake science community could benefit well. Okay, that sounds pretty good, but what about the people who are living on the ground? How do they regard this kind of research? Are they positive about it?
Yep.
Yeah.
The short answer to that is yes. It's a very important question. And actually, I should have prefaced this statement by saying there is a lot going on in terms of community preparedness. And so there's a program called AF8, Alpine Fault Magnitude 8, which has been running since 2015. And it's a very close integration of scientists and emergency management authorities, so the regional councils in the South Island. And there's great work being done on that. And that is really preparing communities to be resilient when this earthquake or other earthquakes happen. So there's lots happening. It's actually not being led by GNS Science. GNS Science hasn't had much going on to do with the Alpine Fault for several years for various reasons, but that work is being done. And yeah, the community value that work, but they also, and this is, I think, quite refreshing, they also value just science for the sake of science, which lends itself a little bit more to this final point. They reckon, they are interested. If we go down there, even in a community of 300 people, we'd get a good fraction of them out for a talk. They live there, they see the mountains, they know what's under their feet, and to some degree, they enjoy being told about this as an interesting natural science laboratory, rather than simply being told, there's a hazard and you've got to prepare. That message after a while gets quite wearing. If you're constantly being told, be prepared for the next big earthquake, after a while you're like, I get it, we're prepared. They are very self-reliant communities. They're going to have to be, because some of them, like Haast, for example, I've mentioned a couple of times, it's several hours to get there from there's only 2 directions, and several hours, 2 hours at least, in both directions. And even a decent storm will cut them off. So if we have a magnitude 8 earthquake that goes through and produces 8 meters of displacement, each bridge will be out, the fibre optic cables will be gone, and they know that. But no, in terms of the sport for the science, I think there's real enthusiasm for taking the just the circumstances they find themselves in and saying, right, what can we do here? And the point I'm making here, this is mostly a point that's hard to convey to government, because the government would say, well, if it doesn't benefit the New Zealand communities, we're not all that interested in funding it. And that's why I think it's a tricky tightrope to walk, because the information that you record in Franz Josef as the Alpine Fault goes whipping through won't be much good for that community's preparedness, but it will be very useful for the communities in Japan or Southern California. And that's a slightly tricky message. To that end, I wasn't going to do it, but we've just created a new degree called Natural Hazard Science and Policy. And the point of this is to address a problem in New Zealand, which is that the authorities responsible for developing policy that pertains to natural hazards, including climate change and coastal erosion and so on, they are finding it difficult to correctly ingest the science. And so being in Wellington, the centre of government, a little bit like Canberra, we feel at my university that we should be really trying to work hard to bridge that gap. Because there's all sorts of good science being done and people are writing interesting policy, but some of the policy is not being well informed.
So you wouldn't change the title to natural risk science?
No, don't even get me started. Don't get me started on that. That's the thing. Don't get me started. There is a whole pipeline from understanding the peril to understanding the hazard to understanding the risk to understanding the policy and planning dimensions. And we chose to come down on saying we're going to understand natural hazards. It's a subtle point. I take it on board, but no, that's what we're calling it. The suggestions were crazy.
All right, we should thank John again. Thanks very much.
Thank you.
And if anybody wants to join us for dinner, please let me know and I'll add your name to the list. And